Hello, here we are going to learn how transistor can be used as a switch. For this, we will use NPN transistor in CE mode, that is common emitter configuration or common emitter mode. First, we will see the circuit of transistor and compare it with switch. Then we'll draw the load line for our circuit. We'll also see how operating point can be shifted on this particular load line. And then we'll see how the transistor's action as a switch gets controlled in this circuit. And lastly, we'll see the applications of this transistorized switch. So here is the circuit of transistor which can be used as a switch. To bias this transistor, we have used two power supplies. One is VCC, which is supplying collector current IC, and another is VPB, which is supplying base current IB. The potential difference between collector and emitter of the transistor is called as VCE. In this particular circuit, emitter is connected to ground, and so VCE is the potential at collector with respect to ground. From positive terminal of VCC to ground, our circuit appears the way it is shown here. We have a load resistance connected to collector of the transistor. Between collector and emitter is going to be our switch, and emitter then is connected to ground. The on and off action of this particular switch will be controlled by the signal on the base terminal of the transistor. If the switch is supposed to be closed, that means collector should get connected to emitter, giving resistance between collector to emitter to be 0, and collector to emitter potential difference also should be 0. When the collector to emitter potential is 0, VCC, that is the battery voltage, will give a maximum current flowing through RL, which appears here as collector current IC. That means now the collector current IC will be equal to VCC upon RL. Whereas if the switch is open, there won't be any connection between collector to emitter. That means there will be very large resistance between collector to emitter, and collector current will be equal to 0, as there is no path for it to flow continuously up to the ground. This zero collector current will not develop any potential difference across RL, and hence collector will be at the same potential level as the power supply VCC, giving us VCE equal to VCC. So let us come back to our circuit of transistor, which we are going to use as a switch. We can write equation for this collector current looking at the closed loop in this particular path. Here we can see that collector current will develop potential difference across RL. Using Ohm's law, we can write the equation for collector current, then knowing how much is the potential difference across RL. Upper end of the resistance RL is at the potential of power supply VCC, whereas its lower end is at the potential VCE, and so collector current will be equal to VCC minus VCE upon RL. The equation for collector current then we can write in a simple way as minus VCE upon RL plus VCC upon RL. The equation IC equal to minus VCE upon RL plus VCC upon RL if it's compared with the straight line equation y equal to mx plus c, where IC is the y parameter and VCE as the x parameter, we can see that minus 1 upon RL is the slope of the line, and VCC by RL is going to be the y intercept of this particular line. As slope of this line gives the value of load resistance, it is called as DC load line. Now let us have a look at what will be the value of VCE at the intersection of this line with the x-axis. The point of intersection of this line with the x-axis will have the value for y parameter equal to 0. Hence, putting IC equal to 0 in this particular equation, we can find that the x-intercept of this particular line will give us value of VCE equal to VCC. The value of x-intercept also tells us the maximum value of VCE in our circuit. The y-intercept of our DC load line should be equal to VCC by RL. That should be then the maximum collector current that will flow in our circuit, and that is the collector current when VCE is equal to 0. This collector value is then called as IC saturation. Load line is a locus of operating point of the transistor in the circuit. Operating point gives us the value of collector current and corresponding value of collector to emitter voltage in the circuit. The value of collector current and corresponding value of collector to emitter voltage in the circuit can be changed by changing base current of the transistor. Thus, by changing base current of the transistor, operating point can be shifted along this load line. Now let us see the characteristic of this particular transistor when we change its base current. At base current equal to 0, the collector current ideally should be equal to 0. But we will find that keeping base current equal to 0, if we change VCE, we will get collector current changing in this particular fashion. This collector current value is denoted as ICEO, that is collector to emitter current with base left open. This current is due to only the minority charge carriers and it will have a negligible value. Part of this graph which comes between the characteristic for IB equal to 0 and the x-axis is called as cutoff region of the transistor. We can see that the collector to emitter current in this region will be less than equal to ICEO. That means it will be approximately equal to 0. Thus, if we select operating point of the transistor in the portion of the load line which comes in the cutoff region of the transistor, the collector to emitter voltage of the transistor will be approximately equal to VCC and the collector to emitter current will be less than ICEO. That means it will be approximately equal to 0. And so, with operating point in the cutoff region, transistor will act as an open switch. If we select IB very close to IC saturation upon beta, where beta is the current gain of our transistor, we will get the transistor characteristic curve with maximum collector current very close to IC saturation value. Now the part of the graph which is between the characteristic for IB equal to IC saturation upon beta and the y-axis is called as saturation region. If operating point of the transistor is in the portion of the load line which comes in the saturation region, collector current of the transistor will be very close to IC saturation and the collector to emitter voltage will be very close to 0. Now, transistor will have collector shorted to emitter and so it will be acting as a closed switch. Let us come back to our circuit of this transistor. Here we are connecting DC power supply with voltage VBB which supplies base current IB. If VBB forward biases base to emitter junction of the transistor, VBE, that is the potential difference between the base and emitter of the transistor, will have a fixed value depending upon the type of the transistor. If the transistor is made up of silicon, VBE will be between 0.6 and 0.7 volts. Now we can write the equation for IB, that is the base current, as VBB minus VBE upon RB. If VBB is kept 0, the base emitter junction of the transistor does not get forward bias and hence we will have IB equal to 0. Whereas if we select VBB a larger value such that base to emitter junction gets forward bias, we can have IB greater than 0. Hence, let us have a look at this circuit once again and see what two values we can select for VBB, which will keep operating point of the transistor either in cutoff region or in saturation region, which will make this transistor work as a switch. If we select a square wave which has the voltage changing between two levels, that is 0 volt and plus 5 volt, we can change base current from a 0 value to a larger value without it taking any value in between. At VBB equal to 0, IB is going to be 0. If base current is 0, the operating point will be on the portion of the load line which is in the cutoff region, and the transistor will act as open switch. Value of resistance RB can be selected in such a way that when VBB is equal to plus 5 volt, IB will be close to IC saturation upon beta. This will give IC equal to IC saturation, and operating point of the transistor will be in the portion of the load line which is in the saturation region, and the transistor will act as a closed switch. We can then see that when VBB changes its value from 0 to 5 and back to 0, the operating point on the load line will shift from its cutoff region to saturation region, and again from saturation region to cutoff region and back to saturation region. It will not stay anywhere in between the two regions, that is, it will not stay anywhere in the active region. Thus we can see that transistor can act as a closed switch when VBB is equal to plus 5 volt, giving us collector current approximately equal to IC saturation and collector to emitter voltage approximately equal to 0. Whereas it can act as open switch when VBB is equal to 0, giving us VCE approximately equal to VCC and IC approximately equal to 0. This shows that we can operate this transistor as a switch where the switching action of the transistor can be controlled by selecting proper base signal. By selecting base signal which is giving only two voltage levels, we are getting output of this circuit, that is VCE, which is also taking only two levels of voltages. If so, why do we need this transistor as a switch? The base signal which we have selected itself is a switch. So let us see the advantage of this transistorized switch. This square wave can be obtained from the output of a TTL IC. For example, a JK flip-flop. The output of this IC can take just two levels, that is 0 volt and plus 5 volt. And the amount of current this IC can source is of the order of few microampere. If we want this switch to operate a relay or a lamp which requires higher current or higher voltage, the output of TTL-IC will not serve the purpose. And hence we need to amplify the current or increase that voltage. And that is done by using transistor, which is then controlled by the signal which is given at the output of TTL-IC. This is how we can use transistor as a switch to operate circuits which work with higher currents or higher voltages, and controlling signal will be coming from the output of a TTL IC. Here we can see a lamp or an LED which works at higher current can be connected in the collector path of the transistor, and it can be operated by using a base signal which is changing the levels between 0 volt and 5 volts and supplying current in microampere. This base signal need not be symmetric. That means it need not supply base current for exactly half the time of this total period. Let us now see few applications of this transistorized switch. Here we have one circuit in which the LED connected in collector branch of the transistor will glow when light falls on the LDR. LDR is a device resistance of which depends on the intensity of light falling on it. When there is large amount of intensity of light falling on it, the resistance of LDR is very small. As the intensity of the light starts decreasing, resistance of LDR starts increasing. When the light is completely blocked, it will have maximum of resistance. By connecting LDR and a potentiometer R the way it is shown over here, we can adjust the value of potentiometer resistance in such a way that when there is large intensity of light falling on this LDR, the potential at point B with respect to ground will have high value, whereas when the light falling on the LDR is blocked, the potential at point B with respect to ground will be almost zero. By adjusting the value of RB such that when the light is falling on LDR, current flowing through the base of the transistor will bring the transistor in saturation region, we can make sure that the LED will glow when light falls on the LDR. This circuit then can be used as an indicator showing that the door of a locker is open, where then light will fall on LDR. Here is a circuit where positions of LDR and potentiometer are interchanged. In this circuit, LED will glow when light falling on LDR is blocked. Selecting proper value of potentiometer resistance R and the base resistance RB, we can make sure that LED glows when there is no light falling on LDR, whereas LED will be turned off when there is enough light falling on LDR. These kind of circuits can be used as burglar alarms by replacing this LED by an optocoupler, where photodiode of the optocoupler will be placed in place of LED and phototransistor of the optocoupler will operate the circuit of siren, which will be completely isolated from this transistorized switch circuit. Here is a circuit where LDR is replaced by thermistor. Thermistor is a device resistance of which depends on temperature of its surrounding. Intensity of the light connected in this collector branch of the transistor will now depend on the temperature in the surrounding of thermistor. These kind of circuits can be used to indicate temperature in different electrical appliances like oven. Here is an example to use this transistorized switch to operate an electrical relay. There is a DC motor which is operated by this electrical relay. When transistor is in saturation region, that means acting as a closed switch, there will be large current flowing through this coil of the relay. That will close this circuit with a motor and the motor will operate. When transistor goes in the cutoff region, that means acting as open switch, the current flowing through the coil will become zero and that will disconnect the switch in the circuit of motor and the motor will stop functioning. I am sure by now you know how this transistorized switch functions and what are its advantages. So now it is left to you to look for some more applications of transistorized switch. Thank you.